Hey guys, today I'm going to talk a little bit about a synthesis by Li. The synthesis is a member of the Securinaga alkaloid family, and the target today is Flueggine A. I'm not sure if I'm saying that right because natural products always have weird names, but in this paper by Li, they published the synthesis of this rather complex-looking molecule, along with the synthesis of uracane B, which we won't cover because of time. And they thought, by analyzing the structure, that this is a dimer of norsecuronine, which is also a securinic alkaloid, which they postulated could be made from this Weinreb amide of proline. So this synthesis features a lot of organometallic chemistry in general, and we'll just jump right in. So first they react this Weinreb amide with a Grignard reagent made from this here, THF 0 degrees Celsius, and 57% yield. They installed a good chunk of their carbon atoms that they'll be using in this for Flueggine A. After this, they attack the ketone with a organolithium compound with a TMS protecting group here, so this alkynyl organolithium compound using cerium chloride as a Lewis acid catalyst in THF at -78 degrees Fahrenheit. And they installed with good stereoselectivity on this step and 81% yield. After this, they used TBAF to remove the TMS protecting group here on the alkyne, which in the next step they used ethyl magnesium bromide as a base to remove this OH group here, and attacked, which could subsequently attack this chlorine group here. So strangely enough, this didn't have any interference here, which is odd, but I think they added this first and stirred for a while and got these magnesium bromide salt here and then attacked after this, and installed the rest of the carbon atoms in the synthesis. So this is all the carbon atoms that we're going to need. We'll remove a few, you'll see in this next step, but next they use a ruthenium catalyzed reaction, and this is a very principal step of this reaction pathway, and I'll talk about the mechanism here in a second. So you can see just by looking here that they lost a lot of carbon atoms, but they ended up forming basically the entire structure of norsecuronine in one step. And so how do they do this? Well, using this ZAN1B catalyst from earlier work, they did what's called relay ring closing metathesis. So what happens? So first we have this ruthenium, which is I represent simply by this here, implied ruthenium, that comes from this ruthenium catalyst, really interesting compound. And they first lose a methylene group here and install ruthenium here. So the reason this happens is because this is primary, so it easily can be, they can easily get metallation here. So this ruthenium that's now replaced the methylene group is in close proximity to this alkene here, which can go under ring closing metathesis, and we lose this cyclopentene molecule here. So now we're at this step, and the ruthenium is installed here adjacent to this ester functionality, and is in close proximity, if you draw it the correct way, to this alkyne moiety here. So this can undergo cyclization, and we end up with a cycloruthenium intermediate, which can donate a double bond here, and end up with this ruthenium bonded to this methylene group here. And we close this 5-membered ring and end up here with a correct stereochemistry. So to represent this, we can redraw this molecule like this to show kind of where we're going with this pathway. And the ruthenium can then coordinate here and we lose, again, perform ring closing metathesis, lose this methylene group here, and we end up with this final product here in the correct stereochemistry. Very interesting reaction. So after this we have product B. Product B is then used, treated with NBS, to install bromine, actually, to install bromine at this position adjacent to this conjugated ring system here. So we installed bromine here, and they used silver antimony hexafluoride and acetone to remove the bot protecting group and induce the cyclization. There's another step that they, another 2 steps they tried for this pathway, for this specific part here, but they found that silver antimony hexafluoride was the best in overall 60% and 85% yield. The next interesting part of this reaction pathway is they finally generated norsecuronine. So they generated one naturally occurring natural product, but in order to get our final product, Flueggine A, they needed to add a few more steps here. So they first treat it with MCPBA, metachloroperoxybenzoic acid, in methanol at room temperature, and they get the amine oxide here. What's interesting to me is that nothing touched this these alkenes here, and that's likely because you have favorable conjugation here. So, and electrons donated by this, an electron rich amine, tertiary amine here. So the oxidation of this amine is favorable. So then they reflux in solvent, and we get a very interesting step here, where we get this 1, 2, 3, 4, 5, 6 membered ring from the amine oxide to this cyclohexene moiety here, or a cyclohexene ring. So I wanted to look at the mechanism of this step as well, because I thought it was also interesting. So scrolling down, they said in their paper, Lee said in his paper, that this proceeded by a 2,3 Meisenheimer rearrangement, followed by a 1,3 sigma Troper rearrangement. So how does this work? So I wrote the mechanism. You can see here, first we have this oxygen group with a formal negative charge attacking this alkene here, which can then translate its electrons here, which can then donate its break this bond and donate the electrons back to the electron deficient nitrogen atom, and we end up with this interesting also 6-membered 1, 2, 3, 4, 5, 6 ring here. And so after this, something you don't see very often, a 1,3 sigma tropic rearrangement that occurs through this intermediate. So you can see here that if you look from here, it looks kind of weird. So I redrew it, and I drew it from the side, leaving out all the parts that aren't necessary. And you can see that there's this 1, 2, 3, 4 membered ring intermediate, where the electrons are going from here to here, and this is then the electrons are going from here to here, and this bond is migrating here. So it forms this cyclic oxonium intermediate, which then ends up at this product. So why does this happen? This occurs because, like earlier I said, this conjugated system here is favored over having these isolated double bonds here. So this, thermodynamically speaking, this is a favorable rearrangement and can occur if you heat it up a little bit. So after that, we oxidize again the nitrogen atom with MCPBA, and this carbon atom here donates a hydrogen atom to this, or a proton to this oxygen atom, and we end up with intermediate C. So intermediate C is then followed by a Diels-Alder reaction with our intermediate norsecuronine, and gives Flueggine A and 77% yield. So this Diels-Alder cyclization, you can see here on the final model, the final molecule, that this nitrogen atom, this oxygen atom, and these 2 carbon atoms, and this carbon atom of this molecule, are all participating in the cyclization. So we have this oxygen atom, which can donate electrons to this carbon atom, which can then donate electrons to this carbon atom right here, which can then donate its electrons back to the electron-deficient nitrogen atom. So this is a thermodynamically favorable reaction, and it doesn't mess with this here because this is, like I said, it's conjugated. This has aromatic character, this part of the ring. So we end up with this final product in relatively good yield. And what's nice about this synthesis pathway in general is that it uses organometallic chemistry, modern organometallic chemistry, and commercially available starting materials that have predetermined chirality to install some complex ring systems that you don't see often made in such simple ways. So making norsecuronine itself was pretty good, but to continue past this and use this interesting 2,3 Meisenheimer and 1,3 sigmatropic rearrangement was an interesting way to install a reactive functional group here highlighted to go through a Diels-Alder cyclization with a natural product that they generated earlier in the pathway. So it's atom economical and an overall good yield. So the Zan 1B catalyst I haven't seen before, specifically this ruthenium catalyst, but it has an interesting structure. And they said they tried several catalysts. They tried the Grubbs Generation 1 and Generation 2 catalysts to get this ring closing metathesis, but they ran into issues. So this catalyst seemed to be the only one that could incite this type of relay ring closing metathesis reaction. So another example of interesting organometallic chemistry. And then of course earlier in the pathway they use ethyl magnesium bromide, they use organolithium reagents, they use magnesium iodide reagents here as well, so Grignard reagents, in a couple of different steps, and all in all, in good yield and an interesting synthesis.